What is up, everybody? Welcome back to my channel. This is Tony, aka One Leetcode One Day. If you're new here, this channel does one Leetcode per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a Leetcode problem I have never attempted before. You heard that right. There is no prescripted answer. We're on the same page here. But don't you worry, I got you covered, and I promise that I will submit a list and average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I may not be better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. If I can do it, you can do it. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking lead codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's coding problem. Today we continue on series 1, everything about dynamic programming, and the problem they're working on is number 53, maximum subarray. So let's click into it. All right, so maximum array, it's a medium problem. Number 53, so it's one of the earliest problems in the LeetCode set. Given an integer array nums, find the contiguous subarray containing at least one number, which has the largest sum, and return its sum. All right. And there's additional information. A subarray is a contiguous part of an array. All right. Example one, nums equals to a list of these numbers. It could be positive or negative. I bet you there could be zeros too. And the output is 6. Mm, right. So we're looking for the subarray that has the largest sum. We're looking for the most number of positive integers, and preferably the larger ones. So there's a positive, negative, positive, positive. Right. So, right, we're looking for subarrays, a part of the original array that is going to give us the largest sum. Interesting. Um, and second example, if it only has one element, of course it's 1. But if it's a negative 1, uh, I don't know, maybe we don't output anything, or we just output 0. Example 3, input 54 minus 178. Well, we're going to take it all, and it's going to produce 23. And constraints, we can have a list of numbers uh, containing elements between 1 or this is like what, 100,000. Yeah. And then the value of those integers can go from minus 10,000 to plus 10,000. Right, so you need to really make sure that your algorithm, whatever you come up with, has a really efficient um, time and space complexity. So we better go no higher than O of n for both time and space complexity. If I can come up with even better heuristic, that is always preferred. So yeah, let's think about it. So this thing right now, if we want to solve it in a DP manner, we need to ask ourselves the following questions. Um, from a previous experience, we know that we need to break down the original problem into sub-problems uh, of basically the same type, with only difference in the number of elements in the list. So, and then we're going to try to find a connection between an original problem and a sub-problem, and find a way to, recursively reuse the solution to sub-problems in order to support a quicker calculation of a more complicated original problem. So that is the first thing that we want to find out. And then once we found some relationship like that, we want to look at its time complexity. Preferably, we don't want to go with O n squared time complexity, because As we've seen a couple of times in our previous lead codes, if we have a time complexity of O n squared, it's going to exceed the time limit for submitting lead codes. So we better have something like an n, O of n. And yeah, we can afford to use some space complexity, O of n, to store the calculation results of sub problems. Um, so yeah, that is an okay-ish thing. But here, I guess the problem is a little complicated because uh, now our sub problem can start from any index and at also any index after uh, the starting index. So definitely, it looks like we could be looking at a space complexity of O n squared in the worst case, because both the starting index and the end index of our subproblem can change from the first index of the array to the last index of the array, or roughly. Therefore, therefore, we might have to store a lot of pre-computations, more than we actually can afford, and it's going to cost a lot. Are there, possible problem-specific insights here that can help us reduce the number of subproblems we need to look at? I mean, the final solution, it can be anything, right? We can take the entire array, or we can take the entire list, or we can take just a small portion of the list. It could be more towards the beginning, it could be more towards the end. There really isn't a pattern here that um, that we can write down to simplify our representation of sub-problems. So, are there like problem dynamics that can be exploited maybe to uh, you know because in the end we're not really looking for a full table of results. We really just need one result regarding the full original problem. So is there a possible way to delete or rotate the memory as we go, so to speak, so that we don't need to store everything, and we just store something and update the storage, and then gradually um, grow our subproblem larger and larger and eventually into the original problem. And that is something I am thinking of. Can we um, can we roll can we roll our storage in a way that you know we don't need to look back? Um, is it possible? I mean, it is possible. Like, I mean, I think you can just you know be brave and say, hey, we're gonna start. Uh, we're only gonna look at subproblems starting from the leftmost element, right? Or the rightmost element. Take your pick. And then we say we only care about subproblems um, that will in a way, expand to the full problem. For example, if we're starting from the left side, we're gonna have this minus 2 as our first subproblem, and then we're gonna grow to minus 2, 1 as our second subproblem, and then we're gonna grow to minus 2, 1, 3 as our third subproblem, and so on and so forth, all the way till we reach, the full problem. And so we're not really going to worry about subproblems that, start on the right-hand side. For example, this minus 5 and 4. Can we afford to do that? Because if we can, then we can reduce our space complexity at least down to O of n, and maybe potentially even down to O of 1. So those are really tempting solutions. So now let's actually start, I guess, start um, start experimenting. And this example one is a pretty good one. It has um, an enough number of elements to be kind of general, and then the solution is kind of a general pick of a substring, a subarray in the middle of it. So I think it's a good one, and oops, we're going to use that and as our first example to experiment on. So we're looking at possible ways to uh, define our subproblems. We don't really need to cover, all possible ways of defining subproblems. Um, we just need one way to define subproblem that help us get ourselves to eventually the original problem. So let's start experimenting with this. We're going to start our subproblem here. Okay. First, of course, we find out, the total length of this array, nums. Call it that. And of course, this is going to be our zeros element and 1 and all the way to n minus 1. In this case, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, uh, equals 8, and minus 1 equals to 8. So we have 9 numbers in this list, and we're going to say our subproblem uh, um, of 0. Well, just according to our previous convention, we actually prefer to start from the last element so that the index of our subproblem actually decreases. That's kind of like a unspoken convention now. So I'm gonna say this is gonna be our s of n minus one, which is s8, uh, and it only contains the last element in it. Uh, and of course, it returns it returns 4, right? Because that's the largest sum. And then we're gonna say Sn minus 2, which is S7. What this means is that it's gonna contain the seventh and eighth element, and it's still gonna be 4 because we're definitely not gonna take the negative number, right? Um, and then we move on and we say Sn minus 3, which is S6 in our case. So it's adding 1 into the mix, but we're probably not gonna take it because if we're gonna take it, we're gonna have to also take the minus 5 in there, and it's more loss than gains. So we're only gonna take the last one still. And then let's move on to Sn minus what? Minus 4, and this is gonna be S5, right? So it's gonna take into account the number 2 there. So we're just weighing our gains by adding a new number, right? So if we add a 2 there, um, it's still not going um, to counter uh, the um, the loss of adding minus 5, even with the 2 and the 1. So we're still going to take 4. And Sn minus 5, which is S of 4. If we add minus 1 into the mix, well, same. We don't need minus numbers, negative numbers. And the next one will be the interesting one because this is supposed to be where we find our optimal solution um, to the original problem. But so it's S3, and it's going to include this 4 here. And if we include this 4 in the mix, and we look at our previous optimal choices there, then we're gonna kind of like weigh in, the gains and losses of adding the 4 here. So previously we only had the 4. So we were ignoring all these numbers here because it was not worth it to add them all. But now if we have a 4 here, if we have a 4 here, um, now if we weigh in the loss and gains, I mean, it'll be like a minus 1, 2, 1, minus 5. So this is 2 plus 1, 3, minus 1, 2, minus 5, minus 3. So it's a minus 3, right? It's a minus 3, and uh, uh, but then we have added 4, so it actually is uh, a better choice if we include the 4 here. So it is a better choice to include the 4 here. So uh, what do we get in total? If we add everything up, it's going to be 5, right? Because we added one more value. But just be careful because the answer has told us this is not actually the optimal. The optimal solution is actually, let's use purple here, is actually to ditch number 4 and ditch the last two numbers and only take these middle 4 numbers, and that'll give us a sum of 6, right? Yeah. Um, so we basically need to, if we want to grow our subproblem like this, we need a recursive relationship uh, to help us find this number 6 by looking at the previous subproblems. So if we really intend to do our subproblem in this way, then we need to convince ourselves that we can calculate this based on the previous results. Can we? Well, so if we look at our previously, if we look at our um, yeah, I'm just gonna highlight this a little bit. If we look at S of 4 here, and it was still 4 because previously it was not worth it uh, to add uh, any other number than the last number. But then when we have added like a positive number into the mix, of course, um, now there are more possibilities. And now, um, so now instead of trying to look at, so we need to, we can then, I guess, move our anchor, or uh, by anchor I mean like the starting and ending position of our inclusion list. So those are our anchors, we can, or pointers. Maybe we can, because we have a positive number now into the mix. Um, Now we can try, shuffle our pointers, either shuffle our left pointer or shuffle our right pointer uh, in a um, in a different way to see if we can find a better result. So, does the value of S4, help us find this solution here? Does it help? Um, well, it doesn't look like it because I don't see there any, continuity in terms of logic to go from S4 and calculate S3. Um, but I think we spotted some problem dynamic that here is interesting. So the problem dynamic goes like this. I'm just gonna use typing now. So we're gonna say we found some interesting problem dynamic, and that is if we um, if we expand our scope and got a new positive number, uh, which is the case moving from S4 to S3. We got a new 4 there, plus 4. Uh, then we can move our pointers, right, to search for the next best subarray, right? What do I mean? Because um, previously, like even on to subproblem 4, I'm just gonna use another number here, another color, probably yellow. So previously when we were at, S4, our optimal pointers was pretty much still this shape of only including the last number. But then once we expanded our scope and included another positive 4 in there, uh, then we can, try to move these two things, right? Uh, and then we want to actually use some kind of algorithm to move to this purple uh, pointers here, to these purple pointers here, which end up in a sum greater than before. Actually, this is the optimal sum for the whole problem. Uh, how do we do that, in a principled programmatic way? Because here's something we know. Like if you include a new number, if it does bring any change at all, um, you're gonna have to end up using the new number, right? Right. Okay, so this is a rule. We're gonna prove it. If a new addition changes anything about uh, the largest current largest subarray, then the new largest subarray has to include, right? Has to include the new number. We can prove this by contradiction because if the new subarray does not include the new number, then why do we have to include it anyway? We could just work on the original subarray and find the larger one ourselves, right? So I think this is a proven rule. We just proved it orally using contradiction. So um, now we can say that if we want to find some hope with this new number, then we better move our left pointer here. Yeah, try something here. See if it gives us any hope. And we basically need to, try this, and then try this, and try our way to the end, right? So kind of like that. Um, we could do that, and we can already formulate, I think, a dynamic programming recursive relationship. It's just that, with each of the new elements added, we need to actually try k numbers of times, to try to find the best match. And that is going to make our time complexity actually uh, O of n squared. We can anticipate that. So although this is a solution, it's not an optimal solution, okay? So guys, we have already found our dynamic programming solution at this point. So don't worry, we will submit something in the end. Now it is time for us to see if we can actually, in one go, optimize this problem, improve its computation efficiency, better than the seemingly O of n square time complexity. So uh, let's see if we can do that. is there a way or something we can exploit to reduce the number of trials uh, after adding one element to determine like which one is the best, right? Do we have like pointers? Yeah, I think I am onto something here. I think I'm onto something here. Um, because because of the fact that any uh any inclusion or any subarray will have a left and a right, yeah, and we already have a left, right? And we just need to the only thing we need to do is to find a right. And before we come to test anything, what we could have done in our previous attempt, in our previous subproblems, is that we could have, started exactly on the right. Let me just change the color. Let's say we're gonna use what orange? Yeah, we're gonna use this orange and say we start exactly uh, on the opposite side. So starting on the right side, and then we work our way leftward to see like what is potentially a good um, right pointer position for our to be tested in our next iteration, right? So then, for example, when we were on S4, so that is when we were here, we didn't know that the next number is gonna be a positive 4, so we didn't know that. Let's assume that we're on this stage of calculating S4. We should prepare something, you know, for the next problem. What we should prepare is to find out what would be a uh, potentially good right pointer if we had a positive number that is going to make some difference, right? What would be a good place to end the subarray? Would it be the last one? Would it be this one? Or would it be this one? So how do we find that out? Is there some kind of heuristic we can utilize to determine what is a good ending point for our subarray before we move on to uh, a new subarray? Before we move on to adding another number into the list to try our new chances. So let's say um, if we know like the last two elements are like 4 and -5, then definitely we can be sure that we don't want we don't want we don't want both of them, yeah, because if we add them both, we're gonna actually have a net gain of -1, yeah, or a net loss of 1. That's not something we so it's like what would you call like negative property? Yeah, so it's like liability actually. That's actually liability. We don't want liability. So we could have determined back when we were calculating S4, we could have determined that we don't want any of the last two to be involved in our problem because it's not an asset, it's a liability to include any of them. Because if you include 4, you have to include -5. So there's more liability or more loss than gains. So definitely we're gonna move our potentially good pointer uh, further left. So is it gonna be this one here? Let me just come on, put a pointer here. Yeah, and then I'm gonna just move it. Is it gonna be this one? 1 here? It could be. Is it gonna be 2 here? Well, we definitely know that it's not gonna be 2 because if we use 2, then we have lost something that we can immediately gain by just adding it to the mix, right? So So just by looking at that, uh, determining if we want to be here or be here, then it's definitely the answer is definitely that we want to be at end our pointer at 1. Okay, but all this can change if earlier down the line we have like a very big negative number that cancels out the benefit of adding this 2 here and the 1 here, then uh, then we definitely will throw those away as well. So yeah, I think I got a potentially working heuristic in my mind to work this problem out. So it's gonna be like that, okay? We're going to for like for example, I'm just gonna copy these numbers down here once again, yeah, and I'm gonna show you the heuristic that I found out that will find us simultaneously a, I guess we call it a best place to end the subarray, you know, yeah, best endpoint. Uh, but before moving on, we're gonna find the best endpoint during each subproblem and prepare that best endpoint for the next iteration. So how are we gonna prepare that? Let me illustrate what we should do. So when we are calculating, uh, you know, Sn equal to Sn minus 1, which says 8, of course, we're going to call this what? Best end point, right? Or best subarray endpoint. Yeah, and I will demonstrate you how to find this best subarray endpoint when we propagate on our more and more complicated subproblems. So when we work on S8, of course, it's just one element. And the best subarray endpoint is, of course, still that one. So it's going to be still number 8, right? That's our best subarray endpoint. We just have one point. That's the only point we know where to end. Uh, and then when we move on to 7, S7, so we included a minus 5 here. And we know that, these two combined are going to be a negative property, a negative value asset. So we naturally shift our endpoint actually to one value before that. So we're going to shift it to actually 7 876. So we're going to actually shift that to 6, right? Yeah. Hoping that, at least by ending at 6, we're not going to have this net loss of 1. And then when we move on to actually Sn minus 3, that is S6, then we're going to include a 1 here. Uh, because it's a positive number, it's a good place to end. So we're gonna keep this, right? We're gonna keep this, and we're only gonna change this prediction if actually this uh, 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 index 6 at index 6 we have another negative value, right? It's another negative asset. Then if that's the case, we're gonna shift it to 5, but that's not the case, so we're gonna keep it at 6. And then we move on to SMA minus 4. Uh, now we have in addition a number 2 here. So where is a good place to end? Well, because this is a negative gain here, so we don't really want to move our pointer further to the left because we're gonna lose the additional gain of 1. So we're gonna stay here at 6, right? And then we then move on to Sm minus 5 where we included a minus 1. So now we need to be on high alert because now we have a negative value. We're gonna ask ourselves, like, is this minus 1 gonna cancel out all the gains that we had so far? Um, and the answer is no, right? We have a gain of 3. We don't want to throw that gain of 3 out by ditching all them altogether. So because uh, minus 1. We're gonna just write some logic here because minus 1 uh, uh, plus the 2 and plus the 1 uh, uh, or plus whatever current gain here. We're probably gonna end up store that value. Current gain here uh, is equal to 2, right? Equal to 2 greater than 0. So we're gonna keep you know um, keep the best subarray endpoint as 6 because we still are sitting on a net gain here. We can tolerate a negative value, so we move down again. And once we move down to this SM minus 6, we look at, okay, oh boy, we have another positive number and it's big. So when we see a positive number, we feel happy, and because the positive number, right? Because 4 is a positive number. Actually, if it's greater or equal to 0, we'll consider it as not bad at least. So we're gonna keep 6, right? We're gonna keep 6 because that means we're only gonna keep gaining stuff by keeping the previous subarray endpoint. So we're not gonna ditch the endpoint. Actually, the only time that we actually ditched our endpoint, for example, transitioning from 8 to 6, is when we found out that the new number is negative. Right, the new number is negative, and it's gonna cancel out all the gains because minus 5 plus our current gain. Yeah, let me just move this number 6 here a little bit to the right. Um, yeah, because this minus 5 plus our current gain is going to be less than 0. So it's going to lead to a loss if we still stay with where we are in our endpoint. So that's why we are going to say, yeah, we ditch that. And we basically throw the hope, toss the hope a little bit backward, hoping that the next number is a positive number, right? So that is our heuristic. And moving from here to here, because at n minus 3 we have a positive number, so we keep it, right? Because the new number 1 is greater than 0, greater or equal to 0, so we keep it. Uh, Also here because the 2 here is also greater or equal to 0, so we keep it. And we just move on, uh, and then here we move on, and here we move on, right? So we keep rolling this endpoint number, and it's only going to take one memory, right? Actually two, because we're storing like this index and we're storing the current gain. So we are storing two values, but it's still going to be very light in storage. So we're going to keep storing things. Uh, and when we add a new number now, we know where to land, right? Like for example, when we know where to end. For example, when we are at subproblem S3, we're happy that now. Let me change to yellow. We're happy now we have a pretty big, well, a positive number. Um, Also, it's pretty big. Um, well, when we have a positive number, uh, we're gonna throw that, we're gonna combine that uh, with the best subarray endpoint that we found in the previous step, which is step S4. We're going to combine those and we're going to calculate the value there. So that's actually how we got it, right? So this number 6 here, it comes from the number 4, which is the new number, right? The new number. We're definitely going to take that, according to this proven rule. We definitely going to take the new number to see if there's any change. Well, if it's a negative number, forget it. If it's a positive number, we pay some attention and we take a look. And then, um, all the way to the best subarray endpoint. Let's uh, let's give it like a symbol, okay? Uh, let's call it, let's say, how do we name it? You know, um, it's an index, right? We're gonna call it ind uh, uh, um, best int best end, right? Int best end, right? From the new to this ind best end or IBN. So we're gonna calculate, which is right now, this is this index is what, 6, right? Wait, index is it 6? 8, 7, 6, yeah, 6 here. The new number is 4, but its index is what? Its index is 0, 1, 2, 3. So um, the index is 3, right? And it's a value of 4. And this IBN index is 6, and the number is 1, right? So we're gonna basically sum all the values in between those two, and that is gonna give us our 6. And I think this wraps up the improved dynamic programming approach with basically two tricks, right? One trick is that we're gonna start from the very end, and we're going to say our subproblem is always gonna include the last element in the original list. This is our custom way of defining subproblems. And then on top of that, we found an interesting, useful heuristic. That is, we can during each step in our iteration, we can actually 100% determine what is the best subarray endpoint for any future potential subarray candidates. And we just demonstrated, some of the rules to update that endpoint. So now we're going to uh, formulate this into some kind of a code, right? Let's see if we can just write it in one go. Now we're going to take the problem description and write it into our uh, Leetcode notebook. We're going to name it. Today's title is going to be Leet 53. And then the problem is maximum subarray. We're going to take also this description and some examples as well into our markdown. And we also want to take, the constraints, which is important. Yeah, constraints. Yep, 10e4, 10e4. Okay, so these are our constraints, our problem description, and example. Now we're going to copy the solution template in Python as our next section. And next section, we're going to include some test cases. We're going to borrow some test case syntax from previous exercises. And now we're just going to use this example one given in the problem set, given in the problem to serve as our first test case. Yeah, we can include more. For example, I think there's another non-trivial example here. We're going to take it and we're going to put it here. Oops, copied too much. I just need to copy the array. So we're gonna take it there. And what do we expect? 23 was it? Yes, it was 23. So that being said, we have our template and we can start working on it. And let's just, write some documentation here. Version 1, we're going to use is it bottom up? Yeah, it's bottom up because we're calculating from the most trivial, smallest subproblem that we can have and build, gradually build back into, the full problem. So it's a bottom up approach, definitely. DP with a let's call it killer heuristic, killer insight, to bring uh, to bring time complexity down. And we expect this time complexity to be O of n. Whoops, to be O of n because of this little insight that we have. Uh, what about our space complexity? Remember, we are complexity. We are storing. Remember, we're storing. What are we storing here? So for storage, let's use a different color. What do we use? Let me see. Dark green? No. White? No. Let's use black. So for storage, we need to store the result of our subproblems. Uh, but hey, actually, I think we can even save that because right, we don't need to save. We don't need to save the result of our um, of the solution for each of these numbers. Meaning these numbers, no, there's no need to save them, right? Is that true? Yeah, because if we were right about the best subarray endpoint, we have done ourselves a favor and we don't really need to store this value at all. We can just, store this current gain and we're gonna store our best subarray endpoint. That's all we want, and then uh, uh, and then we just need to, I guess, store one value like the current, what would we say, like current best, right? Yeah, we're gonna store like a current maximum, and then first it's gonna be 4, and then for the first few rounds of iteration it doesn't change until this step at S3, we're gonna update it with 6, and then moving on we're gonna expect that okay there's no larger value, so we're gonna stay with this number 6. So really we are looking at a space complexity of O1. It actually only takes, storing 3 values, right? Storing 3 values. And then, of course, our time complexity becomes O of n. So thanks to that, we have a space complexity of O of 1. Let's see if we can do it right in the one go. Now, we need to initialize these things, right? So um, int best end, let's say int best end. Let's gonna initialize it as the what is it like? Right, we take the we take the length of the nums array, and then we're gonna initialize it as n minus 1, right? Let's do some documentation here. Uh, how do we name it? We name it the best subarray endpoint. Best subarray endpoint. Yeah, let's call it current, right? Because we're gonna be rolling it. And then what else? We're gonna have also another thing to store, which is like the current gain, right? So current gain. Let's initialize it as 0, right? So current best gain from the beginning of subproblem to end best end, right? So we're gonna initialize it like that. That's all of our storage. And because we're doing a bottom up approach for dynamic programming, we use a for loop to do that. Uh, we use k as our iterator, and then it would mean the index in the array to start, right? So the index in the array to start, that is gonna be, yeah, the index for that's gonna be the iterator. So it's gonna be in range. The first value, of course. Uh, the first one is kind of trivial, but what do we say? So we start from n minus 2, okay? So n minus 2 is the first non-trivial um, index. And then, so this is a starting point. And what is the ending point? We want to end at 0, right? Because eventually we want to go to the first index. Yeah. And step is going to be -1. Okay. So we have the iterator. And what do? We do a few things here. First, find we find this best subarray endpoint. We need to update it. So now let's just walk through this all over again. Um, at first, it was initialized as n-1, as we have already done. Oops, as we have already done that. And then when it comes to subproblem n-2, or subproblem 7, we see that because the new addition is a negative number, uh, and if we sum it up with the all the gains we have so far, right? The gains we have so far is going to be it's going to be a negative asset, so we're gonna have to update it. Huh? But wait a second. I think at this point we don't have a stored. We just initialized the current gain as a 0 in our case, so uh, I think we somehow need to assign 4 to current gain. And the way we do it is actually we have to include n-1 into the loop, right? Because that is the actual step we should start with. All right, so let's do that over again. We actually start from the last element. And the first thing we do is we look at the value of that element and we decide if we stick it into current gain. Basically, we need to update current gain, right? So we have a module 1, module 1, update current gain. So how do we update current gain? So if the number here is if it's less than 0, right? If it's less than 0, uh, if it's less than 0, we don't really, hold on. Yeah, if it's greater or equal to 0, if the value is greater or equal to 0, then can we include it? I mean, if it's exactly 0, then including it means nothing, right? So if it's 0, we can either include it or just not include it. So let's be more, embracive, and let's include it, right? So if it is greater or equal to 0, we're going to include it. Uh, then we can, so if this new number is a positive number, that means we're going to add it to our current gain, right? Plus equal will become, we basically, we're going to add this into our current gain, and this will become our new current gain. Else, right? Else meaning this number is less than 0, then we're going to assess if the damage is too large to force us to give up the value, like, and reset it to 0 again. So we're going to have to calculate, right? If uh, if the number is negative, if the number is already negative, we know that. If it plus its current gain, um, if this causes like a damage, meaning if the sum of that is zero, then we're gonna reset our current gain to zero because we're gonna basically ditch all the numbers that we have stored there so far, and we're also going to move our pointers to the left. Yeah. Okay. So I guess we could really do two things at the same time. Is like update current gain and update end uh, uh, best end. Excuse me. Yeah. I think we can update those at the same time. And in this particular case, we're gonna move this best endpoint pointer uh, to to k minus one to one index earlier in the list because we're seeing that this new added number is actually doing more damage. It's gonna make everything afterwards bad. So we're gonna basically skip all of them. But what if, yeah, in the previous case, if the new number is like a positive or zero, it's at least not bad. It could be potentially good, right? So um, our end best end, what do we do about this? Um, we don't do anything about it, right? Like because we can still be embracive, and we are gonna include everything. We're just gonna keep those new numbers, keep this new number in the loop by not changing uh, this endpoint, right? So, right, we're gonna just keep it. We're not updating it. So, right, so that's the case. And don't forget, even if there's a negative number, there are cases where the negative number is not very large in terms of amplitude. So there's still value in keeping it in the loop uh, because, although it does some damage, but, the numbers after this negative number is lucrative enough that we want to keep them all in there. So yeah, so we're going to update our current gain uh, as unfortunately we have to add this negative number in there uh, to form our new current gain in a way. Uh, so we're actually reducing our current gains. Yeah, and then um, do we do anything about our index? No, we don't do anything about our index. Right. And then that is about updating those two uh, numbers that we need to be stored. So now the only next thing that we need to look at is to add the new number if it's positive. Um, uh, add you know add you know add up the new positive number uh, uh, all the way up to the best array endpoint that that was previously there, right? Uh, right. So we actually do this before updating these two things because these updates are for next iterations. So we actually do that before we updating these things, right? So module one is try the new sum, try the new potential best sum, and we only try that if this nums of k, if this new number is let's say greater than zero, right? Because if it's just equal to zero, it it brings no new like hope at all in adding more, to the overall sum of the subarray. So if it only helps when if nums k is greater than 0, and we're going to try to sum up the list, right? How do you do list sum? Python list sum. How do you do that? Okay, there's a list. There's a sum function that you do it. Okay, simple as that. We like that. We're going to uh, call it sum between nums between what k all the way up to end best end, I believe. Right. So is that how it works? Let me just test something. Oops. Yeah, fine. So what we're gonna do here is we're gonna do a test list. We're gonna do 1, 2, 3, 4, and let's see what is test 1 through 0 through 1. Oh, actually, it's just 1. Okay. So I guess 0 through 0 will throw an error, or yeah, it's an empty list. Okay. So this is your starting index. This is like the end index plus 1. Right. So if we want to sum it from the kth index all the way up to the end best end, then we need to add 1 to it there. And this is our new potential best sum. But to see if it's actually uh, better than the previous best sum, we need to compare it, right? Like if this thing is greater than our previously stored uh, current max, which we initialize as 0, current maximum sum of subarray. So if it's greater than current max, then we're going to update current max with this value here, right? Otherwise, we don't do anything. We could use the list type comprehension, but this if condition is good enough. Um, so that's it. And I think we just finished module 1, which is to try the new potential best sum, right? That's what we do to see if we can find a larger value. And once we've done that, we just store it. And then we try to update these two values, the best or subarray endpoint and the current gain. Uh, uh, yeah, the current gain. We're gonna update that current gain by uh, by judging if the new value that we brought in uh, brings any added value to these two values, to these two quantities. So that's about it. And we have once we finish everything, like run through the for loop, and we got back to uh, 0 here, right? Oh, I guess range. I think maybe we should put -1 here because the way the range function works is that for the second quantity, like for example 5, 0, -1, if we do that, it's going to stop at 1 instead of at 0. Print I, right? If we do that, yeah, you have to make it -1 in order for it to end at 0. So that's what we're doing here. Yeah, it's going to be -1 as the second input. We're going to run all through that, and then what do we have? So at the end of it, our current max is going to be our champion, and we're going to return current max. Yeah, I think that's it. And let's see if it works. Right. Whoops, there's something wrong. Has no attribute jump. What? Where is the jump? Sorry. Oh, okay. Uh,
We are still using the function name from our previous solution. Okay, so here is something. Num is not defined. Okay, there's a typo. It should be nums. No big deal. Okay, another typo. Current gain should equal to nums. Another typo. Wow, come on. There's a lot of typos. Great. They just worked right off the bat. But we're gonna actually try another test case. Remember, we want to try, the singular value cases. Always make sure that you include test cases like this. So actually, we were given one of that here, and the output should be one. All right, so we're expecting one. See if it works. It does work. Okay. So now everything seems to be working, at least for these three test cases. Let's be hopeful and submit it to Leetcode. We passed our first test cases. We passed two two more test cases. Let's submit the code. See if it works. Well, it's already taking way longer than we're expecting. A few seconds has passed. I feel anxious. It's still judging. Yeah, all right, wrong answer. Now let's try this test case. A -1. We are having an output of 0, probably because we initialized a 0. But anyway, let's deal with this test case here. So basically, it's -1, and we're expecting the sum to be -1. But it's actually giving us what? Giving us 0. So let's deal with that. Let's comment out all the previous test cases, excuse me, and use the debug mode uh, to work step by step through it to see what went wrong, right? So we're gonna put our breakpoint there, work our way in there. And now because our array only has one element, so the capital N equals to 1, and we'll get int best and -1. This thing will be 0, and current gain and the current max are initialized as 0. So for k in range of that, you know what? I am just simply going to make an exception, see if it works. That's just a lazy approach, right? We're gonna say, you know, early in the game, before we do anything, if n equals to 1, we're just gonna return whatever uh, whatever number that is before doing anything else. Okay, and that is the solution that we're going to submit. Being an opportunist. So let's judge it again. See if it actually passes all the test cases. Whoops. There's another wrong answer. So okay, so this is actually systematic. Uh, it's not something we can get around with our opportunist mindset. So let's deal with it more seriously. What are we expecting? We are expecting this to be -1, right? To be -1, yeah. Okay, so let's work on that case then. Uh, and we're gonna still set a breakpoint in somewhere, for example here, and then we're gonna work on it. Where is it? Uh, are we are we in here? Yeah, we're in here. And so because the new test case, the first element is -2, second is -1, and the total number is 2, so we have our n equal to 2, right? And we initialize those two values as zeros, and then we're now in our for loop. And in the for loop, the first thing we do is we try the new potential best sum, and we told ourselves that if Um, uh, we started at the last element, which is in this case -1, and we say that if this is like greater than 0, we're actually going to we're actually going uh, to try to see if it's a better current max, right? And if actually the value is like negative, then we're actually skipping that, which is bad, you know. So this is already a problem found. We don't really want to skip it, and we probably should initialize those two with some big negative values. And as we see, you know, the numbers can go as low as 10 to the minus e4. That's what I'm going to use here as our initialization. Minus 10,000 and minus 10,000, because nothing can go more negative than that with the problem range, right? So, and we're going to have to change this logic here. Uh, Instead of saying, hey, if that is greater than 0, then that is when we actually compare it. We should probably say, hey, current gain. Yeah, why don't we actually, huh? Yeah, this is a little bit, we need to think over a little bit um, thoroughly about this. So we either initialize this current gain with a very large, very negative value, and then we deal with um, negative values in a first iteration in the for loop properly, or we initialize those current gains directly with the last element and see how it goes. So there are two approaches. I think I'm going to go with the first, which is to initialize those two things as very negative values, and then we're going to deal with negative values properly in the for loop. I think that's the right attitude. So module 1, try the new potential best sum. So if nums k does end up to be negative, um, what does that mean? That means you still have to um, update our current max uh, with whatever it is, right? It means we still have to update it uh, with whatever it is. Uh, right. Um, so maybe we actually just remove this number, remove this if condition at all. Like we're gonna try every value. Is that no? Is that what we try? I mean, in our drawing, we basically told ourselves, I mean, if we're adding a negative number to into the list, we don't bother calculating it, and that saves time, you know. So we definitely want to keep this thing here, but we just want to be a little bit special about the first step, treating the first step. Right. So I'm thinking maybe we should work on the initialization instead of like initializing this with like a very negative number. We are going to initialize this actually as nums k minus 1, nums n minus 1, which is like the last element. Uh, is that right? Current gain. Well, let's just think about it. Let's not change this. Actually, we need to change this. This is the current max, so the current maximum sum of subarray. So we need to initialize it as, you know, the most trivial sum of the subarray, which is, you know, the most trivial subarray would be like an array containing only one element and it's the last element. So definitely this is going to be nums n minus 1, and we can Uh, and we can initialize it like that. Right, right. So what that does is that it already takes care of the last element in the list. So then it will become okay um, to skip to skip it here, because then we will have the value already stored during the initialization phase. So I think this is how I am going to do it. Uh, let's see if it works. Right, expect -1, and it worked. Now let's just bring in another test. Let's bring the full force of all the test cases, and it still worked. Perfect. Okay. So I think we probably have fixed the bug, but let's just, test them. Okay, submitting again, judging. It's taking some time. That doesn't look good. I hope it's just, oh no, right. It's again a wrong answer. So what are we gonna do? Well, we're gonna add this test case to our mix again and then deal with it. That's the only way to progress. Now, let's see. Right. What? We're expecting -2? Is that is that right? You are -1, -2. You are expecting -1. You're expecting -1, right? -1, -2. You said you're expecting -1, and we gave you -2. Huh. So this has to do with the way we um update our update our index, our current best subarray endpoint. I think we were a little bit biased, and we have missed some cases here. So in this case, when we're dealing with the subproblem of only the last element, of course, we need to, because it's a negative, we need to throw our, endpoint, best possible endpoint, uh, throw it over, throw it into earlier down the list, and we're gonna have to make it 0 at that point. So do we have that? Do we have that kind of behavior? So update in best end, right? We need this to happen, right? Um, because right, this number is gonna be less than 0, and because uh, nums k, in this case, it's gonna be -2 plus current gain is 0. It's gonna be less than 0. So it's going to throw our current gain to what? Current gain to 0. Yeah, we're going to reset that current gain. And then we're going to throw the int best end uh, earlier down the list. So this will become 0. That makes sense. So I think it should work. So somehow our intentions were correct, but we didn't execute correctly. I think that's what's happening. Now let's just use this breakpoint tool to debug. And okay, so we start with this for loop, and our case should start with n-1. N is 2, so n-1 is 1. So we start our k as 1. If we just step, the k should be 1, right? And then the first check for try the new potential best sum. So this is like testing the newly added value, because the newly added value is -2. We have no interest in that. We're gonna just uh, skip that whole thing, and then we're gonna update our current gain, update in best end. That's what we do here. And because this number is -2, we're gonna probably skip the if and just jump into the else condition. And because this is going to be the sum is going to be actually less than 0, we're actually going into it. So our current gain is our current gain is initially 0, and we're gonna keep it that we're gonna keep actually we're gonna do a reset here again, and then we're gonna change int best end into 0, which is indeed what we want to do. And then we go into the next index position, which is index 0, and that is the last index we're ever gonna work with, right? And uh, and then we're gonna go into module 1 to try the new potential best sum. And oh, okay, so that is something that we weren't doing correctly here, because this time we really wanted to update our current max, right? Um, but this condition is stopping us from doing that. We were basically saying, hey, because it's a negative number and we're not expecting it to do any good, to add to our uh, to contribute better, so we're just skipping it. But it's actually not right, because if everything is negative, you're still gonna have to uh, you're still gonna have to maybe take the least negative value out there. So I guess we were a little bit arrogant to say in our rule that because that we're only gonna try positive values as the first value. Because if everything is negative, we might as well pick the next less negative value there. So uh, yeah, so that was my bad. We were a little bit, I guess, arrogant in there. So what I'm going to try is I'm not going to save this, a few steps by having an if condition there. I'm just gonna skip that if. I'm gonna basically compare uh, any new value. We will give any new value a chance to challenge the current maximum, right? So that's what we're gonna do here. Yep, now we have a -1. That's the correct answer. And now let's bring everything in. And it seems correct. Okay, so it turned out we don't really need this line, and it was wrong to keep that line, and we delete that. So now we bring our new solution to Leetcode and submit again, see if it works. Okay, moment of truth. It's actually taking quite long. Okay, yeah, time limit exceeded. Indeed, now you see we have a very long case where we have hundreds of, maybe tens of thousands of numbers, and our time complexity or space complexity exceeded the limited time in Leetcode. But we thought this was like optimal enough, but Leetcode always surprises us, raising the bar. All right, let's see, why is this not so optimal? Can we still improve it? Oh, this is a pretty big surprise. I thought this was a good one, but it turned out that it actually has cost so much time. So this for loop here, we are, oh, I see what we're doing here. So this sums, right? This computation, it is also like gonna take n steps. So so this is something that's gonna cost us. Let's see if there's a way to somehow um, skip this sum, or like in a certain way we're gonna store this sum, and then when we update it, we just need to uh, we just need to try a little bit of something. You see, when we were calculating them here, the number fours, they were based on, the last element, and this element doesn't share any starting or ending pointer. Excuse me, with the optimal answer here in step S3. So it looks like we have to recalculate the sum at each step anyway, because there's nothing in common between the previous step sum and the current step sum. That is a little bit weird. Uh, I guess, well, at least for the first couple of steps when things are not changing, we don't really need to compute the sum at all. Like, yeah, for example, if if this index of best end has never changed, then we don't need to recalculate. Uh, right. So if there's no change, and let me just write that explicitly down. If there is no change in the best end from the last iteration, then we don't we can reuse the sum, reuse the current max from the last step to compute the current max of the current step, right? By just adding nums k, by just adding nums k to the current max from the last step. And we only need to perform completely new sum function when uh, this int best end changes. So this is like the something I found that could potentially drop the complexity, the time complexity a little bit for our approach here. So we're going to implement that logic. Uh, that being said, so we're gonna see, let's see, current gang, right? We're gonna store like a flag, right? Flag uh, end change, right? False. We're gonna initialize as a false, and if we ever update this in the best end, if we ever update this, uh, we're gonna say this flag is now true. Okay, this is a flag to indicate whether int best end has changed in the last step, in the last iteration, right? Um, right. And then we definitely need to update this for all the cases here. So if num's k is greater than 0, so we have a new positive number, then of course we don't update that thing, so this will become false. Or if this new number is negative, uh, but it uh, does not ruin the current gain, then we're not going to change uh, we're not going to change it as well. We're not going to change the end um, the index best subarray endpoint. So yeah, we have a full specification of this value for each case for the update. Uh, Now we need to simplify the uh, new potential best sum calculation. So if actually this thing is true, we need to do that. Then we need to do that, right? It only happens when we so otherwise we just need to compute if nums of k is greater than 0, right? Yeah, if it's greater or equal to 0, uh, then our current max uh, 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 current max equals to current max plus nums of k, right? So if the flag end change is false, which is what we prefer, then we only need to perform one computation to add to find the current max, because our end point position didn't change. We can simplify the computation of the sum by just adding this value. But if the endpoint has changed, then yeah, definitely we have to sum it up. All right, let's see if this works. Whoops, that really messed it up. So, okay, we messed it up. Uh, let's see what went wrong. Current max, current max. Okay, we actually should probably ditch this line because we are biased. No. Okay, this is like throwing ourselves back to debugging now. Right. Let's see. Let's see what went wrong. Let's just start with one test case, okay? Um, for example, let's just start with let's say this one, the second one. I like the second one better because the second one is quite intuitive. So we're gonna do that, and we're gonna put a what? We're gonna put a breakpoint there, and we're gonna start debugging. Now n equals to 5, so we're gonna start k at 4, and the flag of end change is false, right? Flag end change. Uh, yeah, because at the beginning we initialize it as false. What is the endpoint here? Now the endpoint is 4, which is the last one. Yeah. Okay, so how do we compute our current max? The current max is 8. Oh, I see. We're doing a duplicate calculation here. we're doing current max equals, actually right now because we're at the last element, current max should just be nums k. That means, you know what? That means we should initialize current max with 0 in our case. Yeah, maybe that'll help. Let's try that. So if we initialize current max instead of the last element, if we initialize as 0, is that going to help? It does. So, but I'm not sure if, it's going to work for other cases because it was a hot fix. I haven't checked fully the entire logic. Right, for example, this one, the first one failed. So we're definitely going to then work on the test case. But before that, let's just, walk through the full logic, the lines of code line by line to basically streamline the logic to ourselves. Okay, so we first calculate the total length of the nums array, right? We take it as capital N, and then we say for the special case where there is only one element, we just return the first element. Always good. And now we initialize the current best subarray endpoint as the last index, which makes sense. And then we initialize current gain as 0. This is the current best gain from the beginning of the subproblem to in the best end, right? Okay, we'll just leave it like 0 here. I'm not 100% on this, but current max is a current maximum sum of subarray. According to our previous fix, we just said that, um, current max should be 0, and then we're going to work our way back and yeah, assuming it's like that. Current max. So if we are at like the first step and we're just looking at the last element in the list, and of course this flag int change is by default false because we haven't started anything yet, so we don't raise the flag. Um, so we just directly jump to this here. We're gonna say the current max in the first step is just going to be uh, initially 0 plus whatever is in there on on the last in the last element of the list. Excuse me. And yeah, that sounds correct. And then in module 2, we try to update those things, and we say basically if we actually have if the new number is a positive number, which is a good thing, that means we can have new hopes, and we can add that value to our existing gain value because we're gonna keep growing. We're gonna basically append the current gain value with the new value, merge them, and then we're saying okay, we stick with the same endpoint value, so we're keeping the flag false. Um, and else that means we have a negative value uh, down the line. And if it's a negative value, uh, if the new value to be considered is a negative value, then we see if the net gain of keeping this subarray is 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 negative. If the net gain is negative, we just ditch everything and we reset, right? Like we just gonna do reset and ditch the whole subproblem altogether. So we're gonna throw our hope further uh, uh, further backward um, into earlier steps. I'm gonna take some water. Right, we're gonna reset and ditch the whole subproblem altogether. Uh, so we reset our current gain to 0, um, and then we set our end best end to the index before the current one because we're gonna throw everything uh, from the current one onward. And then we're going to set the flag end change to be true because we're now basically cutting out a big chunk of the array from now from the current index onward to the end. It's like cutting a snake, right? Like we're cutting the snake or whatever. And let's not be cruel. We're really cutting noodles, okay? Cutting noodles. We're cutting sausage. We're gonna be cutting the sausage somewhere in the middle, and then we're gonna just throw away um, uh, the section on the right. We're just gonna keep the good part, which is the part on the left. Um, okay, so that is the case when there's negative net gain for adding this value here. Yeah, it's gonna make the entire rest of it bad. And if it's not if it's not the case, like the new value is negative, but it's not so negative, and it's still making the rest of the sausage uh, edible or valuable, then we're going to again um, add that value into our gain, just like here what we did before, uh, right? And then we keep the flag change to be false, and then we move on to our next loop. So that sounds reasonable to me. So let's I think we haven't found the bug here. Let's just set a breakpoint, and then we try to find our problem here by debugging line by line. Now let's restart our kernel to ensure that our debugger is working, and we run it. Whoa, I forgot to put the breakpoint in there. Okay, so here we go. Uh, it's a pretty long problem, but it's okay. We start from k equal to 9, n equal to 9, so our k will start from 8. Yep, and at the beginning, our flag of end change should be false. That's right. So we jump to the simpler calculation of our current max, which is adding, the initialized value of current max, which is 0, to add that to the current nums k, which is 4. So we're expecting now our current max to be 4, which makes sense, right? Because you see, that value has consistently been 4 for 5 iterations in a row all the way until we get here. So let's be patient, right? Uh, all the way until when k becomes 3. So let's be patient. Now we move into module 2, see if everything goes as planned. We will look if its number is greater than 0. It is because it is 4. So we go into the loop. Uh, Current gain, we're gonna say add that, right? So our current gain is 4, which makes sense. Just double check. Yeah, the current gain is 4 because we're just keeping this one value here. And then we move on. Flag and change is false. And then we now go into k equal to 7. Again, no endpoint change. Uh, okay. Okay. So this is the problem because the current max should still be 4. It shouldn't be updated. I mean, although the endpoint didn't change, what we're going to do is to basically just look at the new value here, in this case minus 5, and Let's see. We still need to compare it, right? We still need to compare it with the current max and see if it's a better one. Actually, it could be simplified because if the new value is negative, we don't bother. If it's greater than zero, that's the only way we actually care about it. Uh, so I think we just need to add a little bit of fix here. Else, if that is greater than that, we actually update it. So yeah, I'm thinking I actually keep it. Uh, I'm thinking I should actually keep this line here. I think I should actually keep this line here. So it's only when this number is greater or equal to zero that we have interest in adding it to our table. Yeah. So let's try it again. Well, it's 11 still unexpected. What about if we just use plus? Yeah, it doesn't really make a difference there. So still we have some problem. Let's again use the debugger to debug. We need to reset, restart our kernel, set a new breakpoint here, and run it. All right, we're back at it again. Let's go again. Go over again. N equal to 9, and k should be 8 right now. Module 1, when we try the new potential sum, we go into else. And yeah, because this number is greater than 0, we are going to update current max. Now this is going to be 4. Yeah. And then as for the second module for updating current gain, yeah, because this number is greater than 0, we're going to add that to the current gain, and we say the flag is false. And next is when, k equals to 7, and because there's no flag change, we also take the simpler calculation route. But because now the value here is going to be -5, we're going to skip this altogether. And then for updating current gain, well, the current gain is going to have to be, uh, let's say, the current gain. Do we update the current gain like when we're at k equal to 7? That means we have two elements now, -5 and 4. The current gain starting from the first element all the way to the index best in. Yeah, the current gain is pretty bad right now because it's going to be -5 plus 4, right? Because when we define our current gain, it has to start from the beginning of subprop. We cannot skip any negative, even if we want to. So um, we're saying that okay, if the number is greater than 0, of course we don't change the endpoint, but um, we're gonna add the current gain. I mean, we're gonna add current gain what whatsoever, right? It's not that you can skip it. True, true. So I think that was one more mistake that we made. So current gain is always gonna be like this. I mean, it's not up to you. It's up to us. It's not up to us. We just have to add the new value into the current gain, whether we like it or not, right? Yeah. But you know what? We might update the best end in the end. That's that's something to consider. So yeah, let's just see. So now actually, current gain, current gain, current gain. It's the same in all three cases. We can just take it out and move it outside of the loop, right? Because yeah, in each of these cases we have the same expression, so we might as well just bring it out of the loop, save some lines. Current gain, is going to be we're gonna have to add that, anyway. So in best end, yeah, yeah, yeah. So yeah, so now let's try it again. Still, it's a problem. How are we expecting 10 here? Anyways, let's do the debugging again. We are making progress, you see. Um, Although each time we're finding some new problem, but eventually we're gonna fix them all. So now let's just put a breakpoint here again, and then we're going to loop through. Right, so now we start at k equal to 8, and then again we're in this module 1. Try the new sum. We're going to update our current max into 4. We just did that, and then we move on to the next module, update current gain. We're going to make current gain 4, of course. And then flag, we're not going to change the flag. The best index, we're not going to do that. So now k go to 7, we expect the current max to be still the same, 4, and then we expect our current gain to now unfortunately be what? The current gain now becomes um, okay. So current gain, maybe we should do the current gain um, for the best index. So maybe we should update the current gain after we update the best subarray endpoint, right? I think so. I think so. Because this current gain value that is stored goes hand in hand with this int best end. So if we update int best end, we want the current gain to be calculated on the updated int best end. In this case, we're actually going to update int best end. We're going to throw it into 6. So as we can see, we're going to throw int best end into 6. So we're going to actually update current gain based on the decision of int best end. So right, that's right. So again, we are making a change here. So we're not going to be doing this here, but we're going to update it based on um, whether we have updated the flag of end change or not, right? So if at the end of it flag end change is true, meaning we have decided to roll the index of best endpoint uh, uh, backward, then we need to recalculate. Uh, we need to recalculate current gain, right? We need to recalculate it. So how do we recalculate it? In that case, we're gonna basically, excuse me, we're going to reset it. Yeah, we're gonna reset it. Right. And it's only when it didn't happen, uh, then we will it's only when it didn't happen, then we will just update it like, what did I do? Like we usually do. So if the flag change didn't happen and we still put our endpoint at the same index, that is when the current gain will be a simple addition of the current index, current element value. Right, right. I think that's how you do that. So we're gonna say, update int best end, then update current gain, because that is what you do, right? Um, because you're preparing current gain for the future, for the next iteration. So you want to be most up to date with the uh, array best array endpoint. I think that's the idea here. But somehow we still get a wrong answer. All right, let's start the debugging again, because I just thought we I just thought we made the right decision. Um, current gain. Right, let's just do it again. Now, we put a breakpoint at the same place, and now at k equal to 8, we are going to, so we're at the last element here. And at that last element, we just say current max is going to be 4, and then update index, in best end, the endpoint index. Do we update that? Well, at this trivial last element, uh, we don't really update that, right? And because this value is greater than 0, we don't need to change that. Yeah. I mean, even if it's like negative, even if like the last element value is negative, uh, um, and if it's like just only one value, singular case, we're not going to, then 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 we're not going to trigger this. Yeah. So move on. And there, because there's no mm, endpoint change, so the flag is off. And we just use the usual way of adding current gain. So the current gain jumps from 0 to 4, which which is the case. And then when we have k equal to 7 now, no flag change again. Um, and because this value now is negative 5, and because of that, we don't uh, we don't update the current max, uh, because right now the best way, the maximum value that we have in store is still like just taking the last element. So update the int best end. Um, right, int best end. Now, because it's a negative value, and also because it's so negative that it's making all the values after the current value useless, um, we are going to reset. It's basically, we're going to say this endpoint index, we're going to throw it uh, um, to 6, and then for the flag and change, we say it's true, and because it's true, we're going to reset current gain to 0. Yes. The next one is 6, and for 6, so 8, 7, 6. Next one is 1, and for value of 1, because there is a flag and change. Now it's a new game now. We're gonna have to sum up um, the current one, which is, well, you know what? If we have like a flag change, it only happens when the new the value from the last iteration was negative, and it ruined the whole property onward. then the sum um, then our current max, right? Our current max is simply because we have reset our current max, right? Current max. Um, what is our current max? Current max is 4. Oh, okay. So yeah, current max is 4 because it's the last element. So we're gonna, instead of using this sum, which is probably wrong, we are going to actually, yeah, we found this problem here. Um, Now the new computation is involving only this element 1 here. So we're basically comparing this with the current max. So if this value beats the current max, then the current max is gonna be this. Yeah, that's the new calculation. Right. So let's just move down. Okay, let's not skip this debug again. Um, we were at some values there, and now we have k equal to a. We jump to k equal to 7, right? K equal to 7 is here, and because there's no endpoint change, we are also, this number is not greater or equal to 0. We just skip the current max update phase. We just go into the index best end, the endpoint index update phase. And because this new value is negative and it's going to ruin the rest of the numbers, we actually reset, and we're gonna throw the endpoint index from currently 8 uh, into 6, right? And we're gonna flag this endpoint change, and then we're gonna reset the current gain to 0 and move on to the next iteration. Now we're in iteration 6, and in iteration 6 we're on working on number 1 here, a value of 1. And because we previously had an endpoint change, so the flag is true. So we're basically dealing with a new computation here. And we're looking at the value here. So if this value 1, if it's greater than the current max, then we're going to update the current max. But unfortunately it's not. So because the current max is 4, so we skip it. And then we go to module 2 where we update the endpoint index, the best endpoint index. And because this value is indeed greater or equal to 0, we don't really update the endpoint index, right? Yeah, we don't. We don't throw it further backward. So we're gonna take that if condition, flag is false, and then basically we're gonna use the conventional way of accumulating current gains. Because the current gain is 0, we just simply add 1 to it. It becomes 1. Okay, so now we move on to the number 2 here. For number 2, because now flag is off, is false, we're gonna jump to this calculation here. We're simply gonna add our current number to the current max. Is gonna be 6 here. Wait, huh? No way, this is wrong. Um, we don't really add current max because right, because there's a discrepancy because that current max because the current max is not achieved um, during during the segment of like the current gain, because you remember we have jumped uh, we have jumped that. So what do we do? We're gonna continue to build, build up the sum here, but it, it definitely has to be like a different sum now. So current max, we're gonna need like a max max or like a global max. Yeah, I think we need to do that. Yeah, so we found the bug here. All right, global max. We're going to actually, yeah, uh, global maximum sum found so far. But this current max is going to be current maximum sum of subarray uh, we are currently sitting on, right? Like a hopeful, a array hopeful that we're still sitting on. Therefore, you know what? We're going to change a few things because now, so this is when, we change the tail, change the endpoint uh, of investigation, of interest. Change the endpoint of investigation. Uh, and we're going to be comparing it to the global max, right? Otherwise, we just continue to work on, continue to build on the current max, current local max. Right. And and mm, we also, still want to see if the current max is greater than global max. If it is, we're going to update global max. Right. So in any way, we're trying to compare and update global max in this scenario. It's just that we have like a endpoint change in some cases. In those cases, uh, um, we're gonna compare this with that. Yeah, maybe we can simplify this a little bit because you see, this line has appeared so many times. Um, uh, right. Maybe we can call this, right, right. I think what we can do is we can just update current max to be uh, um, the number here. Yeah, and then we can basically delete this line and just only write it once at the end of the if condition. Right. This is how we make the code a little bit neater. Right. So this first if else condition, what it does is that it checks if we have a new endpoint. And if we do, we're gonna update or reset, the current max with this value right here at the new tail, at the new endpoint. Otherwise, we're gonna continue to build on the current local max, and we're gonna update uh, the current max with that. Um, Is that right? Is that kind of right? Um, so I guess, yeah. Continue to build on the current local max. Yeah. And if the current max is greater than global max, we're going to try to update our global max. Sounds like right. So let's move on to our second module. Update this, then current gain. Uh, Update this current gain. Do we need to update any of the, current max or global max in the second module? No. Uh, right, try the new potential best sum, update current max and global max. Let's try it. Well, we're getting closer, but not quite there. Are we getting an 8? Well, let's try debugging it further. We're getting there. I have no doubt we're getting there. So, yeah, let's just continue with this debug, and eventually we'll get there. So for uh, k equal to 8, right, the first element, which is 4 here, the flag is false, so we just look at this, see if it's greater than 0. It is. We're gonna update our current max. The current max is now 4, and then we see if we need to update our global max, and indeed we do, so we update it to be 4 as well. And then in module 2, we continue to monitor if we need to change the endpoint, and because the current value is a positive, well, we're in no interest of changing the endpoint because we want to include this new value, right? So we just don't change the endpoint, and we're gonna add the current value into the current gain. And now I was thinking, current gain and current max, are they kind of like the same thing now? Uh, it's a little bit different, right? One is like the current best gain from the beginning of subproblem to in best. Current maximum sum of array we are shitting on. So so current gain is like the no-brainer. We just start from the first index of a subproblem and add it up all the way to um, this index best end. But current max is like um, we're gonna still stick with that in the best end, but then if we encounter like some negative values as we progress, then uh, we're just not gonna update our current max. So that's kind of like it. All right. So there we go. So now for this step, our current gain is going to be 4. So now for the next step, when we are at -5, for example, uh, flag and change that is false, uh, and we go into this thing here. Why is it false? Uh, because this, well, it's at k is at 7. Yeah, previously we didn't change the endpoint, so it was false. And then now, if this value is greater than 0, no, it's not. So we're going into, so we're not updating current max, that is, uh, and we're not updating global max. But now, because it's less than 0 and it's going to render the whole gain to be like the new current gain to be negative, um, we're going to reset. We're going to reset the endpoint index, uh, and then we're going to raise the flag. Yeah, here uh, resetting current gain. So our current gain is now 0. Now moving on, because we previously had a flag change, now our current max um, here is going to be 1. And because current max is not greater than our global max 4, we're going to skip that. And what about this nums k? See, nums k, it is flag and change. This value here, it's greater than 0, so we're going to say we're not going to change the endpoint. And because we're not going to change the endpoint, we're going to use the conventional way of adding the current gain uh, with 1. Okay, so now um, k equal to 5. So we're moving on to this one here, number 2, and the flag is false. So we go in here and it's a positive value. So we are actually going to accumulate current max. And it was previously 1, so now it's a value of 3 now. But it's still less than the global max, so we don't update global max. And because it's a positive value, we're not going to change the endpoint. And then we're going to basically say current gain is also now 3. And we move on to the interesting case of k equal to 4, where we have a -1 here. Uh, it's the first time that we got here, right? We debugged into like k equal to 4, so we're making progress. So far, everything seems correct. And then because there's no flag, we basically say, hey, this value, okay, it's not greater or equal to 0, so we're not going to update current max. Our current max is going to stay at 3, and we're not updating global max because of that. So the current max is like 2 and 1, that array. Now, because it's a negative value, now we're going to judge if we want to uh, raise the flag. But since this negative value is not large in amplitude, it's not going to ruin the rest of the current gain. So we're going to say, nope, we don't change it. And we're going to update the current gain with that -1. Remember, current gain, it has to start from the beginning. So although we don't like it, we have to include it. So now current gain is going to be different from current max, right? Because current gain is the sum of these 3 values, and current max is the sum of these 2 values. So far, it's consistent. So let's see what happens when k equals to 3. So we're looking at this number 4 here. K equal to 4, yeah, k equal to 3, and the value is 4, so it's positive. But we didn't have a flag change, so we just directly jump into this. And because indeed now we have a number that is positive, we're going to add this 4 to the current max. So the current max is already 3, so if we add, if we add current max to it, wait, this is where it goes wrong, okay? Because you're skipping that -1 here. Because while current gain keeps that, while current gain keeps that adds that negative value each time. Current max doesn't. Current max doesn't, right? Right. So I think what really we should be doing here is to, instead of using current max, we should be using current gain here, right? Yeah, we should be using current gain here. Indeed. So I'm going to just do that little one fix here. Instead of using current max, we should use current gain because current gain accounts for everything. Right. So let's just try it, but the value is still wrong. That means we need to further debug that thing. That's a fine. We're almost there. We made it to like k equal to 4, so just a few more steps of debug. We'll make it home. All right, so we'll just um, step all the way till we get to k equals 5. Okay, so k equals to 5, 8765. So k equals to 5, 8765 is this one here. And we're having, so previously there's no flag change, and our current max and current gain are both 1. And then because it's a positive number, we have a 2. So we're going to add the current max. It's going to be current gain plus nums, right? And then current max is not large enough, so we skip that. And then we update. Wait, we haven't updated current gain, right? Okay, but we're gonna do it later. So because this number is actually larger, we don't we don't raise the flag, and because we don't raise the flag, current gain is going to be current gain plus um, the number itself. So again, those two are matched. But now when we move on to k equal to 4, this is the interesting part, because now current max will not take into account that value -1, but current gain will. So let's move on, and uh, no flag change because this value is less than 0. We don't update current max. We keep current max, non-decreasing. And then we skip this because current max is not large enough. All right, so, and then we see this is a negative values, but it's not going to ruin the rest of the arrays. So we just say flag is false, and then our current gain will decrease by 1, right? And we move on to k equal to 3, which is this number 4 here. Now, because there's no flag change, we move here. And because now the number is greater than 0, we're going to update our current max. We're going to give it a try. And now here is the critical step that we made a mistake last time. Now, we actually want to add back the -1 negative value while we compute this current max. So we're going to use current gain, which is 2, which is the sum of those three numbers. And then we're going to add number k to it, which is 4. So we're going to get a 6, which is correct. And now, because current max is now indeed larger than the global max, we're going to say now the global max is 6. Wait, oh, I was wrong. It was such a mistake that I just missed out on. All right. You know what? Yeah, we're gonna we're gonna continue debugging to make sure that all the way down to k equal to 2 or 1 or 0, we're still good. So now let's go to the beginning of k equal to 3. Here we are. So k equal to 3. We're here again. Now, there's no flag. Is there a flag change? No. We didn't change the endpoint, so that was flag was off. But then at this point, at k equal to 3, because the number is indeed greater than 0, we update current max, and now current max is large enough to challenge global max. So now global max becomes 6. That's correct. And then move on to module 2. Because this new number is greater than 0, we just say, flag off. Because flag off, we're gonna, update the current gain with this value. So now current gain is also 6. So now we move on to k equal to 2. Okay, that's progress there. And when k equals to 2, um, we're gonna use what? Um, judge flag. Flag is off, but now because the number is negative, we are skipping the current max update, and we're gonna skip that because current max didn't change. Um, Now module 2, because this is a negative value, and -3 is not um, negative enough to ruin um, our current, gain. We're just gonna say we don't change the endpoint, so the flag is again off. But we need to update our current gain. Now we need to take that -3 loss, so current gain will become 3, which is fine. Now we move on to k equal to 1. We're almost getting there, guys. Now there's no flag, so the value here is 1, so it's indeed greater than 0. So we are going to what? Update the current max. Well, current max, actually I don't want to update the current max here, right? Because why? Um, I would think the current max is still 6 uh, because so far we have gone through like some of the changes, and we just took a -3, and now we're taking a 1. So in total, we're taking a hit of -2. So we don't really want to update current max. We want to keep current max like non-decreasing at least, right? So I think for this if condition here, we need to figure a way of um, calculating it. So I think we need to add a line saying, hey, uh, even if the number is greater than 0, it's only when um, the added value is greater than the current max when we update the current max. Okay, so yeah, so I'm actually going to perform that change right now. If that um, and if uh, current gain plus this is greater than current max, that's when we actually update this value here. Yep, because there will be cases where even though we have a positive value here, we're not really updating we're not really gaining much on. We're actually losing something here, right? So that's what I'm gonna do. Uh, I don't know if it's gonna bring us to the right solution. Well, it does. Um, but I still kind of want to walk through the debug to make sure I'm like 100% comfortable with what it is. All right, so I'm gonna spend maybe 5 more minutes to actually do that to make sure that I'm comfortable with the answers all the way uh, down to the last iteration. This is gonna cost some time, but yeah, allow me to do that. Now I'm actually gonna put a uh, breakpoint down here so that I can just use click to bring k down a few values. I want it to stop at 3. I'm comfortable with that. So if it's 3, it's going to be like there. Actually, we can bring it down one more. Now it's at 2, so it's at this value here. Um, Now we have a new negative value, but it's okay. Our flag was off, but this value is negative, so we don't update current max. We don't update global max. But now, uh, because this negative value is not negative enough to ruin our existing current gains, we're going to keep the current endpoint, and then we're going to update current gain with that -3, and we move on. Now we're at k equal to 1, and we have a value of 1, flag off. So if the positive number is positive, now we're here, and we're checking if this current gain, which is now 3, plus the new number, is it going to be exceed current max. In fact, it does not, so we're going to skip that. We're not updating global max. Uh, so flag off, but we're updating current gain with +1, so current gain is +4. Now, finally, we're at k equal to 0, right? Almost there. Flag off, and because this new number is -2, we're not going to be updating any of the maximums here. And yeah, we're updating these indices and current gains, but that's not going to change anything. Um, and then eventually we're going to be going to the end, and we don't want to really return current max. We want to return global max. So with all of that, global max, with all of that, I think I'm now comfortable with this implementation because I think it went exactly as what I intended to go. So I'm going to uncomment all these test cases and I'm testing all of them. Ooh, wow. Okay, so we're still failing some of the interesting negative cases. So let's work on those. All right, let's work on just one of them for now, -2, -1, and find out why it's returning us 0. Maybe we're not paying attention to negative cases now. Um, let's, again, put some breakpoints here. And so the first value is -1. So far, we have initialized all the max and gains as 0. And then now we're starting k as what? As 1. So the last index. Flag off. So we just go directly into this here. And because nothing is positive, and we're not doing anything to update our global max or current max, which is a bad idea if like everything is negative. So we definitely need to, uh, you know, um, we definitely need to put into consideration, all negative cases here, right? We need to code that in because in the current module one of updating the maximums, we're not considering updating the maximum if the value ends up negative. So what exact code shall we fix? Well, the code we shall fix is that if our current, if our current last, our current subarray endpoint is at, here, then we need to, we still need to update our, we still need to update our, I guess, global max, right? Right. We also want to update our current max as well, because currently we're sitting on all negative values, but that doesn't mean we can just be at zero and take nothing. We have to take at least one element, even if it's negative, right? Um, so um, how can we do that? So um, global max. We can actually, exploit this flag and change and actually make it true, I guess, in the beginning, so that we're gonna, in the first step, take this if condition, and we're gonna update our current max with the element here. And then we're gonna go to this if condition to compare current max with global max, and then we're gonna update global max in that one go as well. All right, I think I got it. So this is the simple hacks. We're going to initialize this as true, and then we're going to initialize this global max as a minus 10,000, uh, so that at the end of the day, it'll give us the right value. How about this next one? Right, it is the same. So what about these other original cases? Okay, they return me the true values. I think now we have a similarly correct implementation, guys. It took us quite a few hours, but yeah, let's give it a try. Run code, passed. Run test cases, passed. Submit, accepted. All right. Okay, great. And actually, we we have beaten, most people in the first run. This is great. This is great. Give yourselves a thumbs up, guys. This is the first. I mean, the first accepted uh solution beats, beats others in time complexity. That's kind of like a first for me. So I would consider this a win, and we didn't even look at the solution at all. We figured out this on our own. But it took us a little bit of a twist and turns, and I think we still can optimize this set of code, especially where we have like a current max and a current gain. Ideally, we can just compress those two variables into one, and change our um, if else condition, optimize that a little bit so that we can just use one value to represent both of them. But overall, I mean, um, we lived through all the debug and trial and error, and in the end, this is a good heuristic, because it leverages the bottom-up dynamic programming, right? Um, so I'm just gonna write, uh, leverages uh, 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 bottom up DP, right? Because in essence, it's like that. But then also we have found ourselves some smart tricks to reduce the complexity to ON and O1. Uh, yeah, we did end up, storing quite a few values. Instead of 3 values, we're using 4. We're using, like you see, current gain, current max, global max, end, best end. And also we have a flag and change. So we're storing 5 values to help us navigate through, the different cases here. But still, it's a space complexity of 01 because it does not scale up with the number of elements there. It's always going to be just these 5 numbers. And the time complexity, yeah, we're just having a one for loop. So uh, for n number of elements, we just need to perform this for loop n times. So the time complexity is good. The space complexity is good. I mean, in the end, we made it. So there we go. This is our solution, and it worked. So let's maybe take a couple of minutes to take a look at the solution, see if there's new tricks that we haven't learned. So we're talking about approaches. One, optimized brute force. Of course, that's a lot of computation there, so we're just gonna skip that. Dynamic programming. What is Kanade's algorithm? I don't know. Let's take a look at the complexity. It's ON and O1. Wow, this is pretty good. So maybe it's similar to ours, maybe it's not, but it's worth taking a look. Approach 3, divide and conquer. What does that mean? Slower than the second approach, uses more space. Okay, so it's a heuristic, I guess. Maybe it's not dynamic programming. Excuse me. Um, okay, so it's n log n, space complexity O log n. Okay, so this is inferior. So if you're interested in it, guys, you can take a look at the solution if you have access to it. For me personally, I'm just going to be interested in the dynamic programming and this so-called Kanade's algorithm. See what that is. All right, so let's spend maybe 5 minutes to read what this is. Whenever you see a question that asks for the maximum or minimum of something, consider dynamic programming as a possibility. The difficult part of this problem is figuring out when a negative number is worth keeping in a subarray. Okay, that's a good insight. When a negative number is uh, worth keeping in a subarray. This question in particular is a popular problem that can be solved using an algorithm called a Kanade's algorithm. If you're good at problem solving though, it is quite likely you'll be able to come up with the algorithm on your own. The algorithm also has a very greedy-like intuition behind it. Let's focus on the uh, important part where the optimal subarray begins. We'll use the following example. Right, nums. Okay, we can see that the optimal subarray couldn't possibly involve the first 3 value. Huh, that's a good insight. Why is that? The overall sum of those numbers would always subtract from the total. Yeah, it's a negative asset. So, like, if we start on the left, then if there's a negative value that cancels out all the possible gains to the left of it, for example, this -3, if including it, meaning we're gonna um yeah, I mean, if go past this -3, meaning it's not worth it to go past this -3 here because there's no gain left of -3 that is going to make up the loss of taking -3, right? Same with this -5 here. It's not worth taking anything there. So we can actually just squeeze out this part and squeeze out this part, and take the middle. Right. Therefore, subarray either starts at 4 or somewhere further to the right. Yeah. What if we had this example though? -2, a lot of it. Well, if this is the case, actually this is good. The -3 is worth keeping. As expected, any subarray whose sum is positive is worth keeping. Right, that's true. Let's start with an empty array and iterate through the input and adding numbers to our array as we go along. Whenever the sum of the array is negative, we know the entire array is not worth keeping. Yeah, we would be better off just starting from scratch and throwing the negative asset out. So we'll reset it back to an empty array. However, we don't actually need to build a subarray. We can just keep an integer variable current subarray and add the values of each element there. Uh, okay. When it becomes negative, we reset it to 0. That's kind of like the similar intuition than what we had. Basically, we had this like hard reset. Where is it? Yeah, reset and ditch the whole subproblem altogether if the whole asset becomes like negative asset, right? So we had that thing there. Let's see. So current subarray, max subarray, current subarray, max subarray, current subarray, max subarray. You're taking 1 and minus 3. Okay. Oh, okay. So you have been using minus 2, and then when you move along, you start to ditch. You start to ditch the tail. Okay, okay, interesting. So you're cutting your head and cutting off your head and tail when your head and tail becomes like negative asset, right? In this way, if you're like a snake or lizard or something, when you move on, and when your tail becomes a negative asset, you just chop it off and move on, right? Like that's the kind of like the thing. So I would call it like maybe lizard algorithm because you're acting exactly like a lizard. Because when you encounter some danger and when something bites your tail, making your tail like a negative asset, uh you just get rid of your tail and move on. Um, and now the head is becoming a negative asset, but you don't want to bite off your head. Without a head, you cannot move on. That's kind of funny, but we're gonna keep that negative asset and we move on. And once we now have a positive head again, now what was previously our head can now be chopped off because now that became our tail and it's a negative asset. So we're gonna chop it off. Gonna keep 4 and we're gonna keep minus 1, keep 2, keep 1. So this is actually the best combination here. And once we get into 5, uh, this is a pretty bad head. It's going to not completely ruin it, but almost. Um, so yeah, at the end we're just gonna keep the largest value in our memory and we're gonna use it. Yeah. So I think, you know what, our approach, it grows from the other end because um, I was basing this in a kind of like a dynamic programming way. But then actually, I guess I've said it wrong. Like we actually didn't use the DP. We started with the hopeful idea that we can use DP, but then we just developed this intuition. So we're starting from this end and we're actually growing like that. And this in best end, I think this is our tail, right? This is kind of like the tail in this Kadane's algorithm, and we chop off the tail when it becomes heavily like a negative asset, um, like we like we do have here, like um, yeah, when adding a new value is making uh, 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 yeah, when adding a new value is making ourselves completely negative, we're just going to chop chop everything off and start anew. Yeah. So I think I'm doing exactly or almost exactly the Kadane's algorithm here by keeping our tail um, and then exploring a new head, just kind of like crawling through it and then changing the length of our body. Uh, yeah, and then keeping the memory of global maximum. We have a current max, and we're gonna keep a global max. So I think in principle it's the same algorithm, and but you see, yours is so elegant. That is something very surprising, um, that this solution can be so elegant. Yeah. So, I mean, if you're interested, you can go ahead and think about why this solution looks so elegant and impact, while mine is like almost 30, 40 lines long, right? So maybe that is an optimized way of doing the same thing. But overall, we're in principle doing the same thing as this approach number two, Kadane's algorithm. They're calling themselves dynamic programming, but I just think that we started trying dynamic programming, uh, but then we try to do sub problems and things like that. Um, is it a sub problem? Uh, you know what? I don't think it's dynamic programming again because no, it's not using sub problems. It's kind of like just crawling through, but maybe this crawling through is also dynamic programming. I'm just not sure, but let's just call it Kadani's algorithm. So we made it. All right, that sums up, that wraps up today's video, and I'm gonna make a quick summary here. So today we looked at a problem called Maximum Subarray, uh, and we looked at the problem. We immediately jumped into um, the the solution discovery phase, trying to find a good representation of dynamic programming in this, and then we try to abstract some problems out from it. But then we realized that the dynamic programming approach would be pretty costly in terms of time complexity. So we were pushing ourselves harder to ask, hey, can we actually find some intuition? And we actually found it. That is like there's a few things here, right? Um, so um, the first fact that we found is like if we expand our scope and got a new positive number, then we can move our pointers to search for the next best subarray. Um, if if we expand our scope and got a new positive number, right? Basically, we add one positive number to it, then we can move our pointers to search for the next best subarray. Right, right. But this is an inferior, observation than the next one. So I'm going to actually delete this line because the next point basically includes this point, and I'm just going to use this. So this new point is like this. If a new addition, if a new addition, like yeah, if we go from S6 to S5, things like that, by including a new number at one end of our previous subproblem, um, then if an if that new addition changes anything uh, about the global max, right? Um, then the the new global max has to include the new number, and we have proved this by contradiction. So that was a powerful um, rule that we found. But then we also found another very important rule, um, which is that the next line there, we're gonna basically make it a little bit larger, and it is that if there's no change in um, in the best subarray endpoint. So if we keep the same tail, uh, in the lizard, so to speak, then we can reuse the current max from the last step to compute the current max of the current step by just adding the new head to the current max from the last step. Yeah, um, right, right. So basically, we are we're saying that hey, we can reuse the sum we calculated from previous step, and we don't have to call the max function each time when we try to sum up an array. We can reuse previous computation. That's basically it, and that helps bring down the time complexity to O(n). Uh, right. Um, actually, we only need to reset uh, reset uh, reset current max when the best subarray endpoint changes. Yeah, so the last sentence here means that um, we can reuse previous current max computation as long as our tail position doesn't change. But what if it does? So when we have for some reason ditched all the uh, all the values that we have accumulated up to a certain point because we found like the new number that we added into the mix is like a very negative number, then we basically are going to reset everything, and we're going to because that new very negative number is going to ruin the rest of it, like whatever we found before, because the addition of the new negative number, we're gonna have to ditch it. So we're gonna have to reset everything, and then we're gonna uh, reset the calculation of the current max, and then we're gonna build up from that new reset, and then we're gonna gradually grow in length um, until the next time that we need to reset our our tail our tail position. So yeah, it's like a crawling lizard or crawling snake. Um, any reptiles that whose like tail is expendable. Uh, it's a good analogy. So all right, so that wraps up our problem discovery phase, and then we went on and to coding, and we had this code here, version one. Um, we did go through some um, debugging processes to finally make it correct. But here we are. So this is the code. We had 5 values that we need to store. So our space complexity is like basically 5 values. So it's O1. And for time complexity, because in our for loop, we no longer have complex computations. So the computation doesn't scale inside anymore. It just scales with n. So our time complexity is O(n) for the for loop. So that is it. That is it, guys. So we have wrapped up today's video. Hope you like it or you have learned something from it. Either way, see you in the next video.